All right. Let's do a little bit of a recap of what inverse functions are. Uh, Suppose you have a function f of x that looks like this. All right. The inverse of that function looks like this. So that is f inverse of x. All right. And the big deal is that if you draw a line y equals x, right? Y equals x is a line that's at a 45-degree angle, basically, slope of 1. If you draw a line of y equals x, the function and its inverse are symmetric about that line, right? So could you see that f of x and inverse f of x are mirror images of each other if the mirror was the dashed line? Now, if f of x, if in fact f of x was this, okay, and I drew the inverse of f of x, okay, that's f of negative x. I'm sorry, f inverse of x. Now here's a question for you. Look at inverse, f inverse, right? The inverse function. Is that a function? Is it a function? Does it pass the horizontal, the vertical line test? It does. Okay. Now, suppose this is f of x. Okay. Its inverse will look like this. Is that a function? Not a function. So in this last f of x, which is a parabola, we say that it does not have an inverse function. There is an inverse relation, but not an inverse function, because the inverse does not satisfy the vertical, it doesn't pass the vertical line test. So how would we do that without graphing? How would we know without graphing it? Well, if the inverse is going to pass the vertical line test, the function has got to pass the horizontal line test. So if you look at that f of x, it doesn't pass the horizontal line test. That means its inverse is not going to be a function. In the previous example, it does pass the horizontal line test, so its inverse is a function. Now, let's carry that over to trig functions. Clearly, sine of x, that wave, does not pass the horizontal line test, okay? Because the horizontal line will cross it an infinite number of times. So does that mean we're just going to call it a day and say, okay, that means we can't do any inverse trig functions? Well, no. What we're going to do is we're going to sort of modify the area, the region where we're looking at the sine of x graph, and we're going to take a sample that does satisfy or that does pass the horizontal line test. That process, right, is we restrict the domain to just negative pi over 2 to pi over 2. Meaning, this is negative pi over 2 and this is positive pi over 2. If I just take the part of sine x that corresponds to negative pi over 2 to pi over 2, then that part, only that part, does pass the horizontal line test. All right? So for the purposes of the inverse trig functions then, when it comes to sine, we eliminate anything to the left of negative pi over 2 and to the right of positive pi over 2. Just eliminate it, it's gone. Okay? So now the restricted domain goes from negative pi over 2 to pi over 2. And that means the range goes from negative 1 to 1, as always. Now, let me talk about a little bit more about domain and range. Okay? So suppose you have f of x and you have f inverse of x. Do you remember when last year when we had to solve for an inverse, when you had to find the inverse of a function, what was the first thing you did? Interchange the what? The x and the y. You had to interchange the x and y. So now, in this case, f of x, all right, has a domain that goes from negative pi over 2 to pi over 2. And it's got a range that goes from negative 1 to 1. Okay? If finding an inverse is the same as interchanging x and y, that means the domain, which is associated with the x, and the range, which is associated with the y, are also going to be swapped. So that means for the inverse function, the range will be negative pi over 2 to pi over 2, and the domain will be from negative 1 to 1. Okay? There's something to have in the back of your head as we move on. Now, the inverse sine function is denoted by sine to the power of minus 1, because that's how we do inverse function. It's also called arc sine of x. They are synonyms. They're interchangeable. Now, what does it all mean? Before we get into what it means, this is a function, this is a graph of the inverse sine function. So take a look at the part here, the part that we restricted the domain for right there. If I were to take the inverse of that, okay, so basically if I wanted to mirror it along the line y equals x, it would look like this. So you see how it's an upward scoop versus a downward scoop. That's the inverse, right? It's like they're symmetric around y equals x. But notice what's happened here in the inverse. Negative pi over 2 and pi over 2, which used to be the interval on the x-axis, are now the interval on the y-axis, and the x-axis goes from negative 1 to 1. All right? So it's an interchanged x and y. Okay, what does it all mean? If I'm walking down the street and I happen to see the inverse sine of root 3 over 2 on a billboard, all right, what I register that as is, okay, there is this mystery angle. The sine of this angle is root 3 over 2. What's the angle? 60 degrees or pi over 3. Okay, so that's what it is. If I had been asked sine of pi over 3, I'm given the angle, and I know that it's root 3 over 2. So now it's going backwards. Okay, now this number here is that's the x value. Okay, that's associated with the domain. This number here, that's the y value, that's associated with the range. So what's important is this. For the inverse sine function, what's the domain? Up here. For the inverse sine function, what's the domain? What did we say? Negative 1 to 1. That means the number inside the inverse sine here, that number can only be between negative 1 and 1. So if you have sine inverse of 2, doesn't work. Does that make sense? Yeah. So it can only be between negative 1 to 1. The range, what did we define the range as? Negative pi over 2 to pi over 2. So that range can only be between negative pi over 2 to pi over 2. Now, that is an important thing to deal with. So, take a look at our restricted sine function. I'm going in great detail for the sine. I'm not going to do it for the other ones. That's why I'm doing it for this one. And then for the other ones, we're just going to follow along the same procedure. So take a look at when we restricted the sine. On the left side of the y-axis, on the right side of the y-axis, it goes from 0 to pi over 2. Now on the unit circle, the region between 0 and pi over 2 corresponds to which quadrant? It corresponds to quadrant 1. Okay? Now, the region from 0 to negative pi over 2 corresponds to which quadrant? Fourth quadrant. That means your answer, right? When you have inverse sine of blah, 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 and you want to give the angle that you give must be in between negative pi over 2 and pi over 2. So, for example, 7 pi over 4. Will that be a possible answer? 7 pi over 4. Well, it is in quadrant 4. No, it's in quadrant 4, but it's not between negative pi over 2 to pi over 2. Okay? Look, this is pi over 2. 7 pi over 4 is here. Okay? Even though it falls in the fourth quadrant, 7 pi over 4 is here. It's 1 1/4 pi. All right? So it does not satisfy the proper domain and range. Okay? It can only go from negative pi over 2 to pi over 2. All right, so let's do a couple of examples. Find the exact value of each expression, and I'm just gonna lay it out on the table right now. When you have when you're in doubt, is it radian or degrees? Radian. No more degrees. Degrees are dead to us. That's why last year when I used to do the graphing and all that stuff, I used to do for each degree, I used to do a corresponding radian one, right? Because that's just what reality is. Okay, inverse sine of root 2 over 2. For what angle is the sine root 2 over 2? Pi over 4. Awesome. And that totally falls within our quadrant. I like this visual. Negative pi over 2 to pi over 2, right? So we've got to be within these two quadrants. Okay? All right. Inverse sine of negative 2 pi. For what angle do you get a value of negative 2 pi for the sine? Not possible. Okay? Not doing it. Not possible.
Can you explain what it's like this one between negative? Because it's more than... So you can't even find an angle that's not between negative.
Right. So remember what we said here, that the domain, the stuff inside the inverse sine, must be a number between negative 1 and positive 1. Okay? How much is negative 2 pi? It's negative 6.28. That is not between negative and positive 1. Yes. Yes. All right, yeah.
What if also the inverse sine of pi over 7? Would you like that?
No, not if you're doing it. I mean, you would if you have your calculator available, allowed. If it's on a non-calculator section, it'll be the angles that we know. Cosine then, right? The cosine is going to be restricted as well. But for the cosine, we go from 0 to pi. All right, and that's the part 0 to pi. So, let's see. The inverse cosine function has a restricted domain over 0 and pi. And if we look at the the quadrants for cosine, it goes in which two quadrants? The range is going to be between 1 and 2 because we're going from 0 to pi. Okay? So, never negative pi over 3 because that's not within the quadrants. Never 4 pi over 3. Okay? All right. So take a look at this. Find the exact value, inverse cosine of 1. So for what value is cosine equal to 1? For what angle? I have a 0. So remember, cosine is the x coordinate, right? And it's 1 for an angle of 0. Okay, our cosine of negative root 3 over 2. This is the domain. It's got to be between negative 1 and 1. I have a 5 pi over 6. I have a negative pi over 6. So do we have a consensus that it's the pi over 6's? Okay, so now I have two possibilities. One of those is correct. 5 pi over 6 is in this quadrant. Negative pi over 6 is in the fourth quadrant. Are we allowed to be in the fourth quadrant? No. 5 pi over 6 will work. Okay? Inverse cosine of negative 2. Not possible. Because that number must be between negative 1 and 1. Remember, well, for sine and cosine it is. Remember, sine and cosine have a range from negative 1 to 1. Okay? When I turn that into the domain for inverse sine and inverse cosine, then the domain for inverse sine and cosine must be negative 1 to 1. So the argument for the inverse sine and cosine, the number in that parenthesis, must be between negative 1 and 1. Yes? Are you sure? Okay. All right. Now, inverse tangent function. Inverse tangent function is a little bit easier because it sort of lends itself to, a nice little restricted domain. We just take one branch, all right? And the branch goes from negative pi over 2 to pi over 2, except notice that this time we have open parentheses because of the asymptotes, all right? So we can't hit negative and positive pi over 2. Yes? Yeah? Okay. So, what quadrants will that fall in? 1 and 4 again. Negative pi over 2 to pi over 2. 1 and 4. Can I have an answer explicitly of negative pi over 2 though? No. Okay. All right. So, arctangent of 1 then. What are we feeling? Yes. Huh? What's the angle for which the tangent is 1? Pi over 4. Awesome. Yes. Well, because what's the tangent at negative pi over 4? Negative 1. Right? Okay. So this is pi over 4. Okay, now arctangent of root 3 over 3. Pi over 6. Okay, so for tangent, we can either get a root 3 or we can get a 1 over root 3, which is root 3 over 3, correct? For tangent. Root 3 is bigger. This is smaller. And since tangent is associated with the opposite side, the smaller gets the smaller angle. So it's definitely pi over 6. Awesome. Okay? So let's recap. This pretty much is telling you the same thing over again. I'll go in more detail when we're graphing. I'm going to actually come back to the graphing. Since we're doing the algebraic part first, let's keep doing that. Two other ways of representing the same thing. The first is from your textbook. The second is from another textbook that I used to teach at a long time ago. And I kind of like this one because I think it's a better way to summarize. So when you have inverse sine, right, the domain is going to be from negative 1 to 1. So for example, if you have sine inverse of something, that number here, all right, for the sine, it's got to be between negative 1 and 1. For the cosine, it's got to be between negative 1 and 1. So we can't take the inverse sine and inverse cosine of 2. For the tangent, you can take tangent, it could be inverse tangent of any number, okay? Because tangent has no bound. Now, the other two columns are for the range. So for the sine, it goes from negative pi over 2 to pi over 2, and you have quadrants 1 and 4. Here you have quadrants 1 and 2. And here you have quadrants 1 and 4. And as somebody mentioned earlier, the tangent and sine have the same, it was you. Tangent and sine have the same quadrants. Most common mistake, and this starts here and carries on through calculus. Most common mistake is if I say, for example, inverse sine of, I don't know, negative root 3 over 2, right? Somebody will say the angle that doesn't fall. Like, for example, somebody will say 7 pi over 3. Or no, 4 pi over 3. You see what I mean? Or right? So something that, or they would say something that is in the right quadrant, but not necessarily in between negative and positive pi over 2. Okay? All right, let's do these. Sine and arcsine, function and its inverse, cancel each other out. Remember, how do we define, like, how do we verify functions or inverses, like, in algebra 2? Remember, it's f of g of x has to be x, g of f of x has to be x. So f of g of x, f of f inverse has to be x. So this is just 1/2. Okay? Now, the next case is a little bit more exciting. We're going to do order of operations, right? Parentheses first. So sine of inverse tangent of 1. How much is that? Pi over 4. Minus inverse sine of 1. I just want you guys to be sure. That's all. Pi over 2. Thank you. Okay? Those are the ones that you want to be, you don't want to be doubting yourselves. So, yeah.
Wouldn't it just be, can you just take that out of parentheses because sine of negative sine of 1 would have to be 1?
Is it?
Without that, cancels it out.
Oh no, if you have like sine and inverse sine. Oh, I see what you mean. No, it doesn't distribute that way. It doesn't distribute that way. We'll learn in the, remember, did we do sum and difference identities last year? It's a trig identity. We'll learn it in chapter 5. Okay?
Is the sine and the arcsine just the same thing as like if you have sine or
Inverse. Correct.
Times like sine of negative 1, like on the calculator or whatever, to find that whatever.
Yeah, on the calculator, it is the sine to the power of minus 1 button.
Right. That's the same thing as that.
Yes. Okay, so here, pi over 4 minus pi over 2 is negative pi over 4. And what's sine of negative pi over 4? Negative root 2 over 2. Okay? Now, in this case, we have a sine and an inverse cosine. So they're different functions. What we're going to do is we're going to draw a triangle. Okay? And we're going to start from the inside. Okay. What that's telling me is there is an angle, the cosine of which is 4 over 5. Okay? So, there is an angle, the cosine of it is 4 over 5. So it's a 3, 4, 5 triangle. Please don't show me the work for the Pythagorean theorem for a 3, 4, 5 triangle. Okay? If it's like 11 and 13, fine. But please don't show me the work for a 3, 4, 5 triangle. So now that I have this, now can I find the sine of that angle? Yeah. 3 over 5. All right? Now, what if it's a variable? Again, we draw the triangle starting from the inside. I have a triangle, the sine of which is x. That means opposite over hypotenuse is x over 1. All right? Now, let me call this side B, And I will do this process once, and then we won't do it anymore. So b squared plus x squared is equal to 1 squared. B squared is equal to 1 minus x squared. You with me so far? B is the square root of 1 minus x squared. Yeah, technically it's plus or minus, but this is a link, so it's plus, okay? So it's the square root of 1 minus x squared. So now we know that if it's a leg we're looking for, it's the larger minus the smaller squared. 1 squared minus x squared. Okay? Whenever it's a leg, a missing leg. 1 squared minus x squared. Okay, so now we need the cosine of this. Huh? Correct. It's just the square root of 1 minus x squared over 1.
I can also simplify square root of 1 minus x squared.
It's technically 1 minus x, 1 plus x, right? Which doesn't simplify. But you don't do that. Leave it as 1 minus x squared. That's a more recognized form. Yeah.
The question says to do it as an expression as x.
Right, which this is 1 minus x squared. Okay? All right. Next one. You're on your own. I'll pause this recording for 2-3. Triangle. And if it's a leg we're looking for, we just know that it's the larger minus the smaller and a square root. And now the tangent of this is the square root over x. Okay? And you can get, all sorts of variations. If you end up with a root in the bottom, we're not asking you to rationalize anymore. So you can leave it the way it is. All right? Okay, so in a movie theater, there is a 32-foot tall screen located 8 feet above the ground. All right? Write a function modeling the viewing angle theta for a person sitting in the theater whose eye level when sitting is 4 feet above the ground. So when you're sitting, your eye level is 4 feet above the ground. The screen starts at 8 feet. Okay? So if we take a closer look here, this is you. You want the function for your viewing angle of the screen. So your viewing angle of the screen is the region inside the 2 dotted lines. All right? Now, the way the parameters are defined here is theta 2 is the region that goes from the very top to the solid line down here. Theta 1 is between eye level for you and where the screen starts. Okay? The angle for which you want to write an equation is just the viewing angle. So just the part between the dotted lines would be what? Theta 2 minus theta 1. So your viewing angle theta is theta 2 minus theta 1. All right? Now, when you're solving these, you always assume that the variable or that the symbols, the variables inside the diagram, the constants in the diagram are known. All right? So you just assume that, D is known because that's something you can measure. You just assume that theta 1 and theta 2 are given. Okay? So let's take a look at theta 2, right? How can we connect theta 2 to that horizontal length D? Now, if it's 8 feet here, and if the screen starts 4 feet above you, so it's 4 and 4 here, right? So for theta 2, right, so tangent of theta 2 is going to be 36 divided by d, right? Well, how about theta 1 then? Theta 1 is 4 over d. Okay, that's fine, but what I need is a function of theta. What I need is these solved for theta. Yeah. 36 over, so if tangent of theta is 36 over d, then theta is inverse tangent of 36 over d. Theta 1 is inverse tangent of 4 over d. Okay? So theta is equal to inverse tangent of 36 over d minus inverse tangent of 4 over d. Now, I'm going to throw some notation at you, so calculus is not the first time you're seeing it. We are used to f of x. What that says is there is a function that is called f, and the variable in that function is x. That could be v of t. The function's name is velocity, v for velocity, and the variable is t. Here, my function is theta, and my variable is d. So I can very well say theta of d. Okay, so v of t, f of x, theta of d is equal to inverse tangent 36 over d minus inverse tangent 4 over d. So that is my theta. Now, that's the answer for that one. No, it wouldn't be incorrect, but we're learning new notation. No. So now it says determine the distance that corresponds to the maximum viewing angle. Maximum viewing angle. That means when which variable is at a maximum? What's the variable that corresponds to the viewing angle? Theta or d? Theta. We want the distance. So what is d when theta is a maximum? Well, let's see. Let's graph. Y equals. No, not in radian. So let me put in the function first. So it's going to be inverse tangent 36 over so 36 over d, that's going to be our x, right? Remember f of x, theta of d, f and theta, x and d. Okay, minus inverse tangent of what? 4 over x. Okay, now it's going to be in degrees because when you go to the theater and you want to measure the angle, you don't want to be measuring in radian. So we're going to, first of all, let's switch to degrees. Okay. Now we're going to do zoom 7 because remember before we had that inverse, that secant function and it was all different. Okay. Now let's talk about some reasonableness. Okay. What do you think here? What angle do you think is reasonable for this? 0 to 10? Not so much. Negative 10? Not so much. So what do you think? 50, 60? Okay, so is it going to be less than 0? No. Is it going to be greater than 90? No. No. So why don't we go with 0 to 90? Okay. So window. A lot of stuff. So 0 to 90. Okay, and why don't we make this, I don't know, 45. Okay, that's the, like how many spaces between each one. So like each tick mark will be 45. Right. Now the y, oh, hang on. Sorry, I said this wrong. Oh, hang on. Our x value is the d. Our x value is the d, the distance. So if this is 32 feet, what do you think? This is going to be a lot more, right? So why don't we go from 0 to 100? I did that wrong, sorry. 0 to 100. And the x scale, let's make it 10. Okay, y is our theta. Let's go from 0 to 90. Okay, now let's graph. Ooh, look at that. Right? We have a maximum. We have a maximum. So now, do you have it exactly in the same setting as mine? We'll take a look. If you have a different graph, give me 2 seconds and we'll take a look. Now, these axes, the horizontal axis is d, the vertical axis is theta. Okay? When theta, the question is asking, when theta is a maximum, how much is your d? So let's go find maximum. Second calc for, it is pretty amazing. So we got to go to the left bound. Shh. So I had no idea people were going to be coming in. I didn't even know. It's not really. I'm just. No. I just like, because I had no idea, and then I didn't even realize people were coming in. Anyways, whatever. Now we'll know. I don't know. Okay. Okay, so listen. Determine the distance that corresponds to the maximum viewing angle. So the distance is 12 what? Feet. When theta is 53.1 degrees. All right? Okay, now, I would like for you guys to complete this homework. Now, but minus the graphs. So don't do the graphs.